All right, folks, here we go. Tuesday the 12th. Kind of our last day of notes for this chapter, as tomorrow is a in-class review day, lab start day, all that sort of stuff. So, total mechanical energy, and then also we're going to talk through that work and kinetic energy theorem. Just one more problem so you feel more comfortable with that. All right, so here we go. All right, so in this one, what we've got is we've got a 2.5 gram bullet shot at a tree. It is traveling at 350 meters per second when it hits a tree and slows uniformly to a stop. It penetrates into a tree trunk a distance of 12 centimeters. All right, now here's what I'd like you to do. Pause this, go ahead, try and run it. Okay? All right, so hopefully you tried to run through this thing. If you didn't, I get it. Okay. So we want to start off with a change in kinetic energy. So first and foremost, what we're going to do is we want to add into this thing a little bit of a data table. All right. So what we see here is we've got a mass of a bullet. So when we start to analyze all the stuff that we're looking at, this is our mass right here. Now in grams, it doesn't work. It has to be in kilograms. So we slide this 1, 2, 3 to the left. Because we slide it 3 to the left, that's how we get our 0.0025 kilograms down here, right? It's traveling at 350 meters per second. That's our initial velocity. It comes to a stop. All right, perfect. That's our final velocity. And it travels a distance of 12 centimeters. That's our actual distance. Now, again, because that's in centimeters, we can't use it. Centi is 1, 2 to the left of in order to get it to meters, all right? So if we want the change in kinetic energy, we're going to use our delta KE equation for this one. All right. So we put our mass into 0.0025, and we put in our final velocity of 0, our initial velocity of 350, and then what we do is I just took a half times 0.0025, got this number 0.00125. All right. I took 350 squared, that's negative, all right, and I found out that that is negative 122,500. So my change in kinetic energy here should be negative 153.1 joules, all right? So it then asks for what is the net work on the bullet, right? It's this, boom, and a boom, all right? So our net work here is just our kinetic energy. Now you're going to see here, no work necessary, just an answer and a label. I did steal this from a quiz, from a previous quiz, all right? So just be aware of that, that I would ask that question similarly to you possibly on the test, all right? So delta KE equals negative 153.1 joules. So again, it's losing kinetic energy, right? So it's turning into some other form of energy for us, right? So our net work on this bullet is negative 151. Again, that should make sense because the bullet's trying to go that way and the work is applying against it. So because the work is applying against it, it's going to be negative. When we use our motion in one direction, anything that's acting against our motion, as long as we're getting our way, meaning moving forward, that's going to be negative. All right? Last one. All right? So our last one, it's going to add negative, sorry. Completely forgot about those. Last one now is what force is exerted on the bullet and bringing it to a stop. So because we're not lifting the bullet, because we're not at this point really using kinetic energy anymore, we're just looking for a force. That means that the only equation that's going to work for us is the work equals force times distance equation, right? Because this is going to be perfectly horizontal for us, that's why we don't need a cosine. So we take our 153.1 equals our force times that 12 centimeters in meters, right? Divide 153.1 by 0.12, and the force should be negative 1,276. Again, it's acting against that bullet, try and slow it down and to eventually stop it, right? So that's kind of it for that one, right? Total mechanical energy. This one is kind of crazy. It looks visually intimidating the first time you see it, but I promise you, it's not too bad. You just got to think through some stuff. Okay? So for us, we're not going to have any friction in this one, right? So if we don't have friction, then our total mechanical energy does not change. Again, friction is just going to steal energy from us. But for our purposes, we're saying that we're in a frictionless environment because it's a lot easier that way. All right. So we got a kitty cat who's going to jump. Now, I know it looks like they're jumping to the right. I want you to understand, I tried to get them so that they were jumping down. Okay. So converting kinetic energy into GPE and back into kinetic energy. But the total mechanical energy remains constant, right? Especially if we introduce a laser shark. I know you thought it was only in like the Austin Powers movie, but it is legit. This great white shark somehow was genetically modified to have a laser on its top part of its body. Unstinking believable. If there wasn't enough reason not to go in the ocean, now that there's a creation of laser sharks, oh my dear Lord. All right. So anyway, what we're going to see is we've got a maximum amount of kinetic energy right at the beginning. So right as this thing starts to jump, the kinetic energy is maxed out. A minimum amount of GPE, gravitational potential energy, because at that point, it's not very high off the ground. In fact, it isn't high off of that starting point. Okay? Once it reaches the apex, right? So it jumps up, hits that apex, guess what happens? Now the kinetic energy goes to zero. Again, because for the briefest of brief moments in time, that object stops at the top, right? But because it's at its maximum height, it has a maximum gravitational potential energy. All that kinetic energy, as it started to slow, turned into gravitational potential energy at the top of it, right? Now, as it goes down the other side, what should happen? Well, all that gravitational potential energy should turn back into kinetic energy, right? So just as it's about to come back down and hit the ground, it's going to have that maximum kinetic energy, and it's going to have a minimum amount of gravitational potential energy for us, right? So throughout the process, we see as it slows, kinetic energy drops, but as the height increases, gravitational potential energy increases, right? So if our total mechanical energy is equal to kinetic energy plus gravitational potential energy, what we can say is the initial total mechanical energy is equal to the final total mechanical energy. So this is our total mechanical energy equation, all right? Kinetic energy and gravitational potential energy in the beginning are going to equal kinetic energy and gravitational potential energy at the end. Okay? They will always balance each other out. Without friction, we assume that all of that energy gets transferred directly into kinetic and gravitational potential. Okay? So, the rock throws a 2 kilogram rock exactly vertical with a speed of 11 meters per second. All right? Here we go. What is the rock's, not the actual rock, the actor, kinetic energy initial? What is the rock's GPE initial? Again, the actual physical rock, not Dwayne Johnson. Okay? What is the kinetic energy of the rock at the apex? What is the GPE of the rock at the apex? And then in part E, what is the maximum height the rock will reach? Now, take a breath, because this thing looks intimidating, but understanding what's actually happening through this will make life a little bit better for us, right? So we want to know, what's the initial kinetic energy? All right, so in the beginning of this, as soon as that rock, right, so let me draw my stick figure of the rock, right? So we got a rock right there. He's going to throw that thing upwards, right? Because he's throwing that thing upwards, we want to know, initially, does it have velocity? Yeah, it does. It's got 11 meters per second, right? So, because it has initial velocity, we're able to say, all right, it's a 2 kilogram rock. It's moving at 11 meters per second, right? So initially, the kinetic energy is 120 joules. And that's all imparted from him trying to throw it up. So as soon as that leaves his hand, it has 121 joules of energy, immediately following his hand release. Okay? Part B, what is its initial GPE, right? So again, because we're looking at setting for the rock, this point as our 0 point, right? We ask, what's the initial height? Well, off of the hand, guess what the initial height is? It should be 0, right? And again, notice I'm using y's here just to talk so that you understand the vertical piece. You could use h's here, right? And those work as well, okay? So it's 2 times the g, gravitational acceleration, and 9.8 times the height. So we're saying that this is barely, this is basically 0 meters for us, all right? So our initial GPA is 0. And again, that should be 0 because remember, it's based off of the height. If the height is still 0, it doesn't have any gravitational potential energy, all right? What is the kinetic energy of the rock at the apex, all right? So now what we've seen is this rock has gone from here all the way up to here, and now it is sitting right there. So the question becomes this: is it moving at the apex? The answer should be no, it's not. So when we look at this, what we should see is our velocity here is going to be 0. Okay? So our kinetic energy is 0 joules at the top. All right? So when we see this, what we end up seeing is, what we end up seeing here is that all of that kinetic energy disappeared. Where did it go to? All right? Meaning that it had to be transferred to something else. Well, this is where this equation at the bottom comes into play. So we want to know, what is the GPE of the rock at the apex? Well, we knew that initially this was it 121? Yeah, it was 121, right? And this was 0. Well, we know that this is 0 here in the final time because it doesn't have any velocity. So then that means that at the apex, our final height, or our final GPE, that has to be equal to the kinetic energy in the beginning. All right? So because of that, it's 121, right? So we got basically 121 plus 0 equals 0 plus x, our GPE final. All right? So now that we know how high this, now that we know how much energy it has sitting right at the top of that apex, what we can do is we can figure out the maximum. Right? So again, GPE at the apex is just the mass times the gravity times the change in height. Well, for us, to find out how high it went, we just rearrange it. So we take 121 times 2 times 9.8, right? Because that's our gravitational acceleration for this problem. And we find that the maximum height that the rock threw this rock was 6.2 meters. Okay? So we threw it with a velocity of about 22, 25 miles per hour. And he threw it about, what's that, 19, 20 feet up in the air. Okay? And that rock is about a 5-pound rock. All right, so just a quick side note for you, all right? Consider an object sliding on a horizontal surface, all right? Does friction speed up or slow down the object? Should slow it down, right? When the object slows down, does it have more or less kinetic energy than it started with? Should have less, right? Again, slowing down means it's losing velocity. Kinetic energy is partially based off of the velocity. One would argue that it's mostly based off of velocity. Okay? Kinetic energy is a form of mechanical energy. So if you lose kinetic energy, you lose mechanical energy, right? So then this form of energy has to be transferred to somewhere else, right? That mechanical energy gets turned into heat. So if you ever have taken your hands and rubbed them together, right? What's happening is that you're turning the energy of movement and kinetic energy into friction. And that friction turns into heat, right? And that's what we'll kind of, I wanted to show you a cool picture. All right, so that's our formulas. I didn't update them, but this one is really interesting for me, all right? If you look at that Lamborghini, they're pushing on the brakes so hard that the ceramic brakes are actually starting to glow red. Pretty crazy stuff there for us, all right? Anyway, go ahead, hop out, try working through homework, all that good stuff. I'll probably try and I'll check out homework and see if there's any good examples on there. If there's, I'll put out a practice for you. Okay? Talk to you.